Busy back in the dawn of time, we were doing distance and time graphs at one point, right? So, for example, you can look at displacement. You can look at throwing a stone in the air and it goes up into the air and it comes down, and you've got a displacement or a distance versus time graph, right? Now, it doesn't bother somebody to turn a distance versus time graph into a speed versus time graph. You all understand what speed is, and the fact that speed is part of distance and time doesn't bother you, right? It's just a different way of showing similar information. So for an example like this one, say this was after 2 seconds. The gradient at this point is 0, obviously, and the gradient of your distance time graph, you might remember from year 11, is your speed, right? So what we have is we have a speed, at the time of 2 seconds, we have a speed of 0, and you end up with a speed time graph that looks like this. Now, you don't need to worry about what the graphs look like now. We're going to do that in the calculus, okay? But the point is that there's nothing that really bothers you about the idea of putting distance versus time versus speed versus time, right? It's fine to do both, and it doesn't confuse you. Do you agree? When you did distance and time and you did speed and time in year 11, nobody was fussing like, oh, how can we put distance on the same graph as time? When we did it with, speed, and they are the similar things. I hope you, anyway. So this is a similar thing. In other words, the graph I was showing you yesterday, you were looking at specific individual angles, okay? So you were looking, for example, at 30 degrees. And if you had 30 degrees, we know that the sizes of the triangle that are required to make 30 degrees is a triangle where the sides look like that, okay? So that is just a fixed relationship every single time in order for you to get 30 degrees. And you cannot get 30 degrees unless the hypotenuse is twice the opposite side, and unless the scale factor between the opposite side and the adjacent side is times by square root 3. It's impossible, right? Which you can just take my word for, but that's what trigonometry is. There's a specific relationship between the lengths of the lines and the angle that you generate, right? What you have on this graph over here, this is the graph of y equals sine x. And if you look at this, sine x on this little graph over here, where we are basically looking at the sides that are involved, is y over r, as we know. Y is 1 and r is 2. And so in this case, sine of 30 degrees is equal to a half. Do you agree? That's what it says, right? If you go here and you put the 30 degrees inside here, then you are going to be there, right? There is sine of 30 degrees, and sine of 30 degrees is a half. So I'm trying to get you to understand the relationship between these two graphs, right? It's just like the speed, distance, time thing. They're showing you some elements of the same thing, but not exactly the same elements, right? So on this one, what we have is we have the lengths of the sides versus the angle. That's what we're basically looking at over there, right? So the x and the y values are in fact lengths of sides, and then we're also including the angles as part of that. Over here, what we have is every single time you put an angle into here, okay? So I put 30 degrees in there, and I get out a value of a half. What we have is we have the ratio of the sides versus the angle. Does it make sense? Do you see that they're very related things, but not the same thing? So the one diagram is the actual sides that make that angle, and the other one is showing you the ratio of the sides that make each angle. So if, for example, you're looking at sine of 90 degrees, right? You are busy saying there that the ratio of y over r is 1 over 1, right? So that's the ratio that makes that particular thing. You have to have your hypotenuse and your y value be the same. In other words, if you were looking here, okay, you take this arm, the 2, and it would be up here at 2, wouldn't it? Right? If you swung it through, it would be up here at 2. And so your angle here is now 90 degrees, okay? And when we've got this little 90-degree triangle over here, the y value is 2, and the r value is 2. So sine of 90 degrees is going to give me 2, is going to give me 2 over 2, which is equal to 1, right? So if you go over here, this is plotting the ratio is 1. You go over there, you plot it against 90 degrees, and you've got the ratio plotted against that. So if you went and looked at 45 degrees, for example, so 45 degrees is there, right? That tells you that for 45 degrees, you need a ratio between, that's about 0.7. You need a ratio, so this is saying sine of 45 degrees is approximately 0.7. And by 0.7, they mean opposite over hypotenuse. And if you pick up your calculator and try it out, you should get more or less that. I mean, I'm guessing from a graph, so it won't be exactly. Please check your calculators in degrees. But sine of 45 degrees says square root 2 over 2, which is the exact form. And if you push the SD button, you're going to have 0.707, right? And so on. Okay, so what you're getting is the ratio. So I'm just trying to help you to see the relationship between these two graphs so that they don't bother you. The one is, if I want the angle 30 degrees, what sides am I going to need in order to build it, right? On the Cartesian plane. The other one, also on the Cartesian plane, is the angle itself against the ratio, okay? And I was showing you that when we were doing a half, that we got exactly the same answer when we had 150 degrees. In other words, if we drew the triangle over here and we had 150 degrees here, this y value was still 1, this r value was still 2, and so that sine of 150 degrees still gives you a half. And you can see it because that is here, right? When y is equal to 0.5, this is my one answer, which is the 30 degrees, and this is the second one in that particular part of the domain, which is the 150. Do you agree? Showing you very clearly what the other diagram says. It's saying to you, I'm getting exactly the same answer, I'm getting exactly the same ratio for two completely different angles. And of course, it's sine, so they're in the first quadrant and the second quadrant because those two give you the same ratio, and this is ratio against angle, right? They give you exactly the same ratio, and it's the same sine, right? We know that there are two angles down here that will give us the same ratio but with a different sign, right? So over here, your y value is now -1, your r value is still a half, and this is the quadrant with 180 degrees plus theta. So if you're going to go and add 30 degrees to 180, that's 210. And if I go here to 210, that is 210, right? Same ratio, but now it's negative 0.5 instead of positive 0.5, right? If I go into the fourth quadrant and I say 360 degrees minus 30, so 360 degrees minus theta, I'm going to get 330, and that is going to be this angle over there. So this is showing you that what's on the cast diagram is true, right? They're all giving you 0.5, aren't they? But some of them are giving you negative 0.5 and some of them are giving you positive 0.5. Which one is which? Obviously, if you draw the graph, you can see it. But you can also go back to the cast diagram and you know sine is positive there and positive there and negative there and negative there. You learn it off by heart, you know it in your sleep, and it should be logical to you, right? And so we're expecting the third quadrant. This is first quadrant, second quadrant, right? 0 to 90, first quadrant. Second quadrant, 90 to 180. Third quadrant, 180 to 270. Fourth quadrant. And so we're expecting the two fourth quadrant ones to obviously be negative. And obviously, this graph is going to carry on into infinity. So if you were to extend it, it would go up and down into infinity. And every 360 degrees, there'd be another answer that's the same, right? Which again makes sense on the cast diagram, because if you have a ratio there for 30 degrees, if I go around another 360 and I end up with 390, of course 390 is the same angle as 30 degrees. Do you agree? You've just gone round an extra time. And so if I go and look further along in that graph, if I go another 360, I'm going to get the same angle. And the same thing happens on the negative side. So over here, if you look at negative 0.5 over there, that is negative 30. Because negative 30 is the same angle as positive 330, right? So I'm just going to erase this because it's getting hell of a messy. But if we have positive 330 sitting over there, so there's positive 330 starting over there, going all the way around, that's 330. Then surely this is negative 30 degrees, right? So they are the same angle. They will have the same ratio. It's still 30 degrees, so it will still be 1 to 2 because that's what it makes at 30 degrees. And it's obviously this one over here. And then there's another one over here, because if we go and we add on, if we go over here and we go some more on the negative side, that takes us to this one over here, which is in the third quadrant. And because it's inside the third quadrant, of course, it's negative. And if we take away some more, we end up in the second quadrant, and now we're back to it being positive. And if we take away some more, we end up back in the first quadrant, right? So if you have negative 330, that's clearly the same thing as 30 degrees. So over here, I've got negative 330, which means I've gone all the way around here, around here, around here. And if I go negative 330, then that is the same thing as 30 degrees. So, of course, again, they have the same ratio, which is there, right? So you can see that these two graphs work together. They're not telling you anything different. They're exactly the same thing, right? And you can see another very important thing is that these angles are repeating every 360 degrees. There's one there, add 360, another one there, right? This one over here, add 360, takes you to there, right? This one over here, add 360, takes you to there. This one over there, add 360, takes you to there, which makes sense because the period of sine is 360. It repeats itself every 360 degrees, which makes sense from the cast diagram as well. You can see you're back where you started every 360 degrees. So everything is making sense, right? If you look at the cosine graph, exactly the same thing. For cosine, we are positive in the, I'm sorry, I just wrote the wrong thing, in the fourth quadrant and in the first quadrant, right? Because any angle that we draw in the fourth quadrant or the first quadrant will have the same x value. So again, if we look at 30 degrees, this one is square root 3 for both of them. The x value is square root 3 for both of them. The y value is 2. So cosine of 30 degrees is adjacent, which is square root 3, over hypotenuse, which is 2. And so, of course, you're going to get the same thing in both of those quadrants because it's positive and it's the value is square root 3, so how can it be different, right? So if I'm just going to put square root 3 over 2 and convert that into a decimal fraction so I can prove something to you. So that is 0.866. So in other words, that is the ratio that you require in order to get a 30-degree angle. So if we go and we look on this graph at 30 degrees, we should get 0.866. So there's 45 degrees, 30 degrees is about there somewhere, right? And if you go across and you look at the ratio, it will, without any doubt, and you can try this out in Desmos if you want to prove it to yourself, be 0.866, because that's the point. That is the ratio that is required in order to make a 30-degree angle. If we want to look at the ratio that is required to make a 60-degree angle, we can go to 60 degrees, and the ratio that is required is 0.5. Now, again, that should not come as a surprise to you, because do you remember when you were in year 11, we discovered that cosine of 60 degrees is the same thing as sine of 30 degrees. They give you the same ratio. And that makes sense because you're taking the triangle and flipping it around. So if you're in this quadrant over here, if you're in over here, and you have an angle that is 30 degrees, then this will automatically be 1, that will be 2, and that will be square root 3 without any doubt, right? If you draw a triangle at 60 degrees, what happens is that's still 2, but now they switch values. This one becomes 1, and this one becomes square root 3. Definitely, that's how you make a 60-degree angle. So if you look at this one, if I'm saying cosine of 60 degrees, which is the pink one, then I'm going to be saying the adjacent side, which is 1, over the hypotenuse, which is 2. If I say sine of 30 degrees, then I'm going to be saying the opposite side, which is 1, and the hypotenuse, which is 2. So everything is making sense on every level, right? Again, looking at the cast diagram, you see how we have a positive value when we have cosine is equal to 30 degrees, and a positive value when we have cosine is equal to negative 30 degrees, because that's this quadrant here, where cosine is positive, and that quadrant there where cosine is positive, exactly as we're expecting, right? Our equivalent angle in this quadrant is going to be 180 degrees minus 30, so that is going to be 150. And so if you go to 150 down here, you are going to end up with the same answer, which is the 0.866. There's 150. But it's now going to be negative 0.866 because you're in the third quadrant, right? And if we go into the fourth quadrant, it will still be negative. It will be down here. So it will be 180 plus it, which is 210. And that's again going to give you the 0.866. So do you see that everything makes sense on this thing? If you look at the tan graph, we know that tan is positive in the first quadrant and the third quadrant. Makes sense because in the first quadrant, we're saying x over y, and for 30 degrees, for example, that would be, y over x. So it's tan of your angle, which is y over x. So your y value is 1 and your x value is square root 3. Our equivalent triangle in this quadrant, our y value is negative 1 and our x value is negative 3. So negative divided by negative is a positive. Obviously, you're going to have something positive, right? And so they're the same. And you can see it. So if we go and look at 30 degrees over here, there's 45. If we go and look at 30 degrees, it's about there somewhere. And we're going to get the same ratio if you go and you look at plus 180, which puts you in here, right? So if you add 180, you're going to automatically be in the third quadrant, and you're going to get exactly the same answer, and there it is. And if you go around another 180, you're going to get the same thing. And if you go backwards, if we go in the negative direction, there it is. There it is. Same answer every single 180 degrees. And the negative version down here in the other quadrants. So if you look at this, this is first quadrant where we know tan is positive. Then we've got second quadrant where we know tan is negative. There it is, right? Third quadrant where we know tan is positive. There it is. Fourth quadrant where we know tan is negative. There it is, right? If you're going backwards, starting there, first quadrant, at least fourth quadrant is there, right? Then you're going there, third quadrant. Second quadrant, first quadrant if you're going backwards, right? And sure enough, tan is positive in the first quadrant and the third quadrant like it has been for everything. Do you agree? So we are going to reduce everything. The reductions that we happen to know already are this. The first thing that you would do with anything, so they say to you, reduce tan 220 degrees, right? You are going to find out which quadrant it's in and what the acute angle is. So immediately you use your cast diagram. It's going to be the easiest way. You know that's 0, that's 90, that's 180, and that's 270. So I know that I'm in that quadrant. Do you agree? No doubt I'm in that quadrant, yes? Because it's between 180 and 270. That's not going to take any brains at all. Tan in that quadrant is positive. I know that off by heart because I know my cast diagram. Okay? To work out the angle, it's always 180 degrees plus theta in this quadrant, which you're going to know off by heart. In other words, this is the same angle as tan is 180 degrees plus 40. So the acute angle is 40. And it is positive because we are comparing tan in the third quadrant where it's positive to tan in the first quadrant where it's positive. So they're both positive, right? If I have sine of 300 degrees, first thing I do, I work out which quadrant I'm in. I'm obviously here in the fourth quadrant, right? Between 270 and 360. What we do for that quadrant is we say 360 minus theta. So you say this is the same thing as 360 degrees minus 60. You don't go and turn it into something different. It's still 300. 360 minus 60, still 300. That means my angle is 60 degrees. So this is sine of 60 degrees. However, sine is negative in the fourth quadrant and positive in the first quadrant. You're turning it into a first quadrant angle. So that is negative sine 60. And if you go and you try it in your calculator and you put sine 300 in and negative sine 60, you will find they're the same thing, right? So for each and every angle, you will work out where it is and reduce it using either 180 degrees minus theta or 180 degrees plus theta or 360 degrees minus theta. Negative theta is the same as this. So negative theta, if we go our angle, is going to be the same as 360 degrees minus theta, which should make sense, because if you go this way and you go 360 degrees around, it should make sense, right? It's the same angle. So if they say to you, let's reduce sine of negative 120 degrees, which is a nastier question. First of all, you're going to work out which quadrant you're in. So if I'm going 120, I'm going negative 90, I'm in the third quadrant. Do you agree? So this is negative 90, this is negative 180. That is not hard to find. I know for a fact I'm in the third quadrant. I would then switch to the positive angle. In fact, I'd just switch to the positive angle straight away. It's going to make your life much less confusing. So let's rather just switch to the positive angle. That is the same as sine 240. Do you agree? They add up to 360, people. If I go around this way, that's 240. If I go 120 this way and 240 the other way, that's 360. This is not hard. So I think the best thing to do with negative angles, turn them into the positive angle first. Positive angle, not too surprisingly, is still in the third quadrant, right? So this is 180 over here, and this is 270 over there. Our angle is firmly in the third quadrant, okay? In the third quadrant, to convert the angle, we use 180 degrees plus theta. You never use 270. You never use 90. If you do, you're going to switch between sine and cosine in unfortunate ways that you don't want to think about. Please don't do it, okay? So this is sine of 180 degrees plus 60. That's not very hard. So this is the same angle as sine of 60 degrees, but I'm comparing a first quadrant angle to a third quadrant angle. So it's negative sine of 60. And that will be the same angle. And that's what you're doing today. I'm going to write, oh my God, this thing is monstrously long.